Hello everyone, this is Mr. Kozlowski and welcome to Learning Target 1 Lecture Part B. This will be talking about electrons today, specifically electron configurations and dot diagrams. So what do students need to do for Learning Target number 1B? Students are going to have to identify the electron configuration for any atom. They're going to have to draw electron dot diagrams, and then they'll have to take this knowledge and apply it to determine the ionic charge of an element. And basically, I'm going to give you a hint. Electrons are the key to a lot of the things that we talk about in chemistry. So please keep that in mind. So before we get into electron configurations and all the other skills that students have to do, I want to talk a little bit about some history. And we talked about models of the atom in the first lecture and how there was many different models, and one person that developed one model of the atom was Niels Bohr. He was a chemist and he developed the Bohr model of an atom. And there's a lot of chemistry jokes, oh, Bohr model is boring and stuff like that, but basically what he proposed is a way to understand these simple atoms and why they're stable and why bonding occurs, and it's all due to electrons. And what he proposed about these electrons is where they can be found within a stable atom. We know that electrons are found outside the nucleus, but specifically where, we don't know exactly in science. However, Niels Bohr proposed this idea of orbits or energy levels, which are areas around the outside of the nucleus where electrons can be found. So here's an example of Bohr's model, and this one specifically is for the element silicon. And if we look, we have three different energy levels here within the model itself. And each energy level, in order for an atom to be stable, must be full with electrons. And how many electrons an energy level can fit varies depending on the energy level. The rules go like this. In the first energy level, a maximum amount of electrons that can be found are 2. So once the first energy level is full with 2 electrons, another energy level is made if there's more electrons. So for example, number 2 level, all right, let's say we had 4 electrons, 2 would go in the first level and 2 would go in the second. Any other level outside of the first level can hold 8. And so the second level can hold 8, the third level can hold 8, the fourth level, and so on, can hold 8 electrons. We call this in chemistry the rule of octet. If you think like an octagon is a shape that has 8 sides. Octet simply means that this rule, that energy levels can hold up to 8 electrons in a specific atom. So if we look here, we have silicon. Silicon has an atomic number of 14, so that means it has 14 protons and 14 electrons. And if you can look in this model, you can see that we have 1, 2 in the first energy level. Now we represent the energy levels as these orbits or rings, and you've seen some of this before in some of the activities we've done in class, but that's what we signify as the area. They don't necessarily orbit around in a circle, they're moving kind of all over the place though in reality. The second energy level can hold 8, so we have 2 here. We have then 8 electrons on the outside in the second energy level, so that's a total of 10. And then we have to go to a third energy level here where it holds 4. All right? And so we have 2 plus 8 plus 4. That's going to give us our 14 for silicon. Electron configurations are ways to determine how many electrons are in each energy level. So we don't necessarily want to draw out Bohr's model every single time for identifying how many electrons are in each energy level. So what we use is a diagram called the bookshelf. And this method is going to be the way we use to properly communicate the electron configuration, or how many electrons are in each energy level. So if we have silicon here, it's very simply put, here on the right hand side we have the energy levels. And again, silicon has atomic number of 14. So in the first energy level, which is the innermost energy level, we know that the rule is that it can hold 2 electrons total. So what we do there is we put 2 electrons there in our first shelf on the bookshelf. Then we know that we have to get to 14 total electrons. We're then going to put 8 in the next one. So 2 plus 8 is equal to 10. We are then left over with 4 electrons because we have 10 of the 14. So we would have 4 left over into the third. And that would be a proper way that you write the bookshelves. And these are pretty relatively easy once you get used to it and understand that, all right, we have this bookshelf, we have this how many electrons, we know that, all right, the first energy level can hold 2, the rest can hold 8. And as long as you know that, you should be able to complete these electron bookshelf diagrams. Now, we had 14 electrons in those in the electron configuration for silicon. The important electrons are the outermost electrons in that electron diagram, our configuration, which is our bookshelf method. And there was 4 left in the outermost shell. Those electrons are called valence electrons. So valence electrons are the outermost electrons of any atom. And these are the most important electrons because they are involved in forming bonds with other atoms. Valence electrons determine a lot of things and basically provides a lot for us in terms of chemistry. They are going to determine the number of bonds an atom will have. They will determine the number of unpaired electrons that we'll have in a dot diagram, which I'm going to show you here in a little bit. And they also determine the formal charge of the atom as well, which we'll discuss later on this unit. If an atom is neutral, its number of valence electrons equals the main group number. So for example, carbon is the main group number 4. Carbon's right here on the diagram. Its main group is number 4. It's going to have 4 valence electrons. So we talked about a little bit about properties of the periodic table and how they're arranged in periods and rows and columns and whatnot. Well, this is one of the ways it's organized, that, all right, any element in the main group 4 is going to have 4 valence or outermost electrons involved in chemistry. To signify these valence electrons, we don't want to draw a whole bunch of electrons in these diagrams or in these configurations. So what we use are called electron dot diagrams to properly signify the valence electrons. They are a simple way of displaying these valence electrons, and the rules are fairly simple. For an electron dot diagram, what we're going to do is the steps, we're going to write out the chemical symbol. So here in this chemical symbol right here, we have sulfur. You're going to write out the chemical symbol, and that represents the nucleus of the atom. All right. Again, this is a model. Models are not completely accurate. I know nucleus has protons and neutrons, and we're not going to signify that in an electron dot diagram because we're concerned about electrons. Then you must find out the number of valence electrons. Sulfur is in main group 6. It's going to have 6 valence electrons. You're going to then draw 1 dot to represent 1 electron around the symbol in this configuration. Each side must have 1 electron before putting them into pairs. So what you tend to do is when you draw these, you will start on one side. So sulfur, I'll start on the bottom here. I'll go to the next side, to the right, 1. Then I go to the next one, and then the next one. Each side must at least have 1 before you can fill in the pairs itself. All right. So if we had, for example, if we had an element like carbon with 4, we're going to have 4 dots on the outside, not 4, 2 on one side and 2 on the other. All right, because we want to have them all sides filled in this configuration in this model to represent the valence electrons. You will get plenty of practice drawing these out in class as well. So to review, electron configurations are going to show you how many electrons can be found at each energy level of an atom. We are going to use the bookshelf diagram to represent our electron configurations. You have to understand that valence electrons are the electrons that are the outermost energy levels, and those are the ones that are involved in bonding and allow us to do a lot of the chemistry that we do later on in this unit. And then finally, electron dot diagrams are a way to display how many valence electrons are available for any atom. So that's Learning Target 1 Part B. Please let me know if you have any questions. and you'll get a lot of practice in class drawing these configurations and dot diagrams. Thank you.